A 400-meter steel hull carries 24,000 containers across oceans, powered by an engine taller than a 4-story building. And 90% of everything you own probably rode on one of these to reach you. A container ship is not really a ship. It is a floating industrial plant. Stay till the ending. Old-school sails are coming back on a modern hull. A container ship a mile out at sea looks like nothing, a small dot on the horizon. Pull the camera closer and the trick breaks. The Ever Ace measures nearly 400 meters long and 61 meters wide, with a gross tonnage over 235,000. It carries 24,000 TEU. Standing next to one in port is a different experience entirely. Try walking the length of one and your legs give out before you reach the funnel. Tugboats floating beside it look like bath toys. The ship-to-shore cranes barely clear the top of the container stacks. The hull just keeps going. Out at sea, with nothing to measure them against, these vessels vanish into their own scale. 3 container ships sit near the port of Piraeus, Greece. From this distance, they look like plastic models on a gray, hazy table. Around 90% of the world's goods rides on ships like these, and hardly anyone on land ever looks up from their phone long enough to notice. This is what building one actually looks like from ground level. A dockyard the size of an airfield. An army of engineers. A vessel measuring 400 meters end to end, capable of carrying more than 18,000 containers loaded with electronics, chemicals, meat, and machinery. The corridor these ships work is Asia to Europe, worth around $316 billion in yearly business. Building a Triple E is a 38-week race against the calendar. The yard gets one attempt. There is no rebuild if the schedule slips. Twin engines, each delivering over 40,000 horsepower, drive the fully loaded hull through the water at 16 knots. Every part of the vessel is planned to the millimeter before a plate is even cut. Watch what it takes just to move one piece. The block being lifted stands over 30 meters tall, taller than a 10-story apartment building. It weighs 2,200 tons on its own. A floating crane rated for 3,600 tons is needed to hoist it, and even that machine tilts backward under the load until the block levels it out. 24 blocks like this make up a full Triple E, and each one starts life as a flat stack of raw steel plates. Everything in that block began as raw steel sheets stacked on a shipyard floor. Plates get cleaned, primed, cut by CNC plasma to the exact shape of each hull section, and marked with part numbers. Subassembly follows. Then real hull work begins. Rust never quits, and the ocean keeps the receipts. Ships used to be riveted. The rivets kept quitting. Modern hulls are welded. Over 5 kilometers of thick erection joints on a single 400-meter vessel. Manual welding would take 20 passes per joint. Robotic electrogas machines finish each seam in one, bonding steel into watertight joints in milliseconds. Instead of building the ship bottom-up like a house, the yard prefabricates 24 megablocks and welds them end to end. Each block takes 2,200 tons of steel. Plasma cutters slice metal at 16,000 degrees Celsius. Robotic arms weld it. The block arrives in dry dock, ready to fit the next one. Now watch what happens when 24 of those blocks finally meet in a dry dock. The HMM Dublin, one of 12 mega 24,000 TEU container ships, grows visibly week to week. A floating Goliath crane lifts each block into place, while surveyors track alignment down to the millimeter using total stations. That precision matters more than most people realize. A hull this long accumulates tolerance stack-up along its length, and small misalignment between two blocks can affect the shaft line, container bays, and hatch covers hundreds of meters away. Every joint gets non-destructive tested before the next one begins. When the ship is nearly ready, the hull gets its final livery painted inside the dry dock, because no other place in the yard is big enough. 20 years from now, will humans still oversee this kind of construction, or will most of it run under drones and autonomous welders? Where do you see it going? Some hulls have to be built around something before the outer plates even go on. This one wraps around an 18,600 cubic meter LNG tank. Assembly of the full hull took 14 months from first block to launch. Building a ship inward is a different puzzle entirely. The moment a half-finished hull leaves the dock for the first time is called the semi-launch. Water floods in through the caisson gate, the ship rises off its supports, and a thin bulkhead is the only thing standing between the interior and total flooding. 2 tugboats pull the shell into the bay so the next ship can start building right behind it. Watch the whole sequence compressed into a minute. An aerial time-lapse follows, one Tripoli from empty dry dock to a distinct hull silhouette painted in light blue and red. Cranes swing, blocks arrive, welders work through the night under floodlights, and the vessel takes shape layer by layer. An empty hull is still just a hollow box. The moving parts that make it a ship come next. With the hull sealed, the ship needs internal architecture to keep thousands of containers exactly where they belong. It starts with cell guides in every cargo hold. Vertical steel rails welded into the structure that let containers slide down into precise positions, corner-locked against each other and against the ship. Get the guides right, and stacks stay stable even when the vessel rolls hard in heavy seas. Get them wrong, and a container can jam mid-drop or transfer sideways load into the wrong part of the hull. Above the holds sit the hatch covers, enormous steel lids that seal each cargo bay from seawater while carrying containers stacked on top of them. A quayside crane lifts and places each cover using a spreader, the same tool that handles the boxes themselves. Every hatch cover has to be strong enough to carry the weight above, tight enough to shrug off breaking seas, and light enough for the crane to swing it. That is the design puzzle in one sentence. Hatch covers wear out. When they do, they get removed from the vessel and shipped to a laying facility with 440 cover capacity, then rebuilt, UTM measurement, plate cropping, new sockets installed, blasted and painted, rubber seals renewed. A cracked hatch cover on a loaded container ship stops being an engineering issue the moment lawyers get involved. Once containers stack on deck, physics starts working against the ship. The stacks can climb 9 or 10 containers high. Hundreds of tons of steel and cargo perched above a rolling deck. Wind pushes them sideways. Wave motion swings them. Any container that shifts even slightly transfers force straight into every locking point below it. That is what lashing hardware exists to prevent. Twist locks, small mechanical fittings, connect the 4 corners of each container to the ones above and below, locking them into a rigid tower. Longshoremen work each corner by hand during loading, engaging and releasing the pigtail locks with poles from the deck below. Then, lashing rods and turnbuckles connect the lower stacks back to the ship's structural lashing bridges. One badly seated twist lock in a stack of 100 can be the difference between an on-time arrival and containers ending up on the bottom of the Pacific. Not everything on a container ship fits in a container. For Project Cargo, 4 pressure vessels weighing a combined 214 metric tons. Cranes and specialized rigging move each piece from ship's hold to dock in a carefully planned lifting sequence. Cargo operations at this scale require the ship's crew and terminal team to communicate down to the meter. Every ton hanging in the air is a lawsuit waiting for a bad decision. Before an engine can be machined, the steel itself has to be almost impossibly clean. Bed plates, crankshafts, and engine frames start life as ingots that were vacuum arc remelted. A slow process where the ingot is remelted drop by drop under vacuum, taking up to 48 hours to eliminate dissolved gas, porosity, and inclusions. The result is an ultra-clean alloy that can survive inside a low-speed marine diesel for decades. A dirty ingot at this stage guarantees a cracked crankshaft 20 years later. Clean metallurgy is the actual price of a long service life. A marine crankshaft is not a scaled-up automotive part. For a low-speed 2-stroke ship engine, it can weigh over 300 tons and run 20 meters long, forged from a single ingot to survive torsional stress and metal fatigue over decades at sea. Manufacturing starts with open-die forging, heating the ingot white-hot and hammering it into rough shape under presses generating thousands of tons of force. Then massive lathes and boring mills cut the crank pins and main bearing journals to tolerances measured in hundredths of a millimeter. Get it wrong. At 300 tons and the crankshaft rings like a bell every time a piston fires. That sound goes straight into the wallet of whoever paid for the ship. Say you're crossing the Pacific and the main engine develops a fault mid-ocean. Would you rather have engineers on board fixing it, or an autonomous engine that shuts down and calls a tow? Now watch what happens when a marine engine is built. The 12X92DF is the most powerful Otto-cycle engine in the world. Assembly starts with the bed plate, then the massive crankshaft lowered into place by overhead crane. Frame columns rise around it. Cylinder liners drop in one at a time. Each cylinder is roughly a meter across, big enough to walk into if it were empty. The valves, injectors, and turbochargers are fitted after the liners are locked into place. The whole engine ends up taller than a 4-story building, and every part of it was fitted by hand. A modern dual-fuel marine engine can run on both traditional fuel and cleaner alternatives. In this time-lapse, a 100-ton crankshaft is lowered into a partially assembled block. Frame box follows. Cylinder frame follows that. An EGR module for exhaust treatment gets fitted in. Each cylinder here is 95 centimeters wide. Walk through this video once and try to find the human for scale. Before any engine like this leaves the factory, every subsystem is tested in isolation. Engineers design gas admission valves on CAD, prototype them, then run them on test rigs for thousands of hours to validate pressure control and injection timing. Then the main engine is assembled from those proven subsystems on the factory floor. Fuel injection systems, lubrication pumps, cooling loops, turbochargers, exhaust manifolds, each one gets bench tested before assembly. A ship at sea does not get a warranty call. The fix has to be right the first time. All that torque still has to travel down a shaft, through bearings, past a stern seal, and into a propeller before it becomes thrust. And that thrust starts with one bronze casting spinning at the stern. A robotic arm mills the propeller pattern from EPS foam. Sand molding builds the negative shape. Up to 18 tons of molten bronze pours in. After cooling, CNC machining shapes the blade foot. A robot grinds the surface. A worker hand polishes the final finish. A blue fit test confirms the mating surfaces before assembly. Not every propeller has fixed blades. A controllable pitch propeller rotates its blades in real time to match speed, load, or maneuvering. Better fuel efficiency, better low-speed control, better response. Fixed pitch is simpler. Controllable pitch is more expensive and more capable. Every ship owner picks a side. Even after a propeller is installed, it can be made more efficient by shaping the water flow going into it. On the Santa Rita, a 7,100 TEU container vessel in Rotterdam, crews retrofitted a twisted fin duct in front of the propeller. The device pre-swirls the water flow, letting the propeller extract more thrust from the same shaft torque. Reported energy savings? 3%. The retrofit itself is a proper engineering job. Divers and surveyors 3D scan the stern geometry with a total station. Prefabricated fin components arrive by truck, get measured against the scan, and are assembled on scaffolding around the ship's stern in dry dock. Every weld gets magnetic particle and ultrasonic tested before the fin is lifted into final position and welded onto the hull. Big container ships mostly rely on a straight shaft and propeller, but other vessel types use something different. An azimuth thruster rotates the entire propeller pod through a full 360 degrees, letting the ship walk sideways, spin on the spot, and hold position offshore without external help. Container ships get shaft lines. Cruise ships and offshore support vessels get pods. Different problems, different tools. Around all of it, an engine room has to keep every subsystem running around the clock. An engine room is where everything the ship needs to stay alive gets packed into one steel-walled compartment. On the world's first methanol dual-fuel cargo vessel, crews first lower a green methanol generator module into position, then the main dual-fuel engine onto its foundation. Cooling water, piping snakes overhead. Fuel lines run along the walls. The whole space is monitored from an engine control room where operators watch temperature, pressure, RPM, lube oil, cooling flow, exhaust, and vibration in real time. One missed alarm can turn into a stopped engine mid-ocean. which is the maritime equivalent of your car dying on a highway with no shoulder for 500 miles. On an LNG-powered ship, the engine room supports a fuel system unlike anything on a diesel vessel. LNG has to be stored at -163 degrees Celsius in a cryogenic tank insulated by 27-centimeter polyurethane panels. Double-wall piping carries the gas to the engine at the far end of the ship, with gas detection and ventilation running constantly. Honestly, the LNG cryogenic system is the most impressive piece of engineering on any modern container ship, and almost nobody on land has heard of it. Once every internal system is set, the ship comes back outside for its coating. Electrostatic application charges the paint droplets, so they cling to the hull like magnets, creating an even, super smooth film that reduces drag through the water. Less overspray, less waste, less dock cleanup. A smoother hull burns less fuel every day of its life. Coatings are engineering, not decoration. Anti-fouling coatings are one of the quiet revolutions in maritime engineering. For decades, marine growth on ship hulls added huge drag and destroyed fuel efficiency between dry docks. The invention of self-polishing copolymer paints in 1974 changed that. Coatings that slowly polish themselves in seawater, staying smooth and biocidal for years. The next step was foul-release coatings, non-biocidal surfaces so slick that fouling organisms cannot grip long enough to attach. Modern silyl acrylate and copper acrylate systems now compete side by side. A dirty hull can raise fuel consumption by 30%. Getting the paint right is worth millions per ship, per year. Painting done. Dock floods. Ship floats out. A 350-meter methanol dual-fuel vessel, the first of 12 sister ships, 16,200 TEU capacity. Undocks with the deckhouse forward and the funnel aft, giving more cargo space than a conventional layout. Tugboats guide the hull into the bay for final outfitting. Sea trials are the final exam. The Maersk MC Kinney Muller runs at full engine load in open water, testing speed, fuel consumption, turning circle, and crash stop distance. Instruments record every vibration. Class surveyors watch every gauge. Everything perfect in dry dock still has to prove it on real ocean. Once delivered, the ship enters the trade lane it was designed for. The Margrethe Maersk arrives in an Asian port with a city skyline in the background. The Edith Maersk follows at another terminal, assisted into position by tugs. A truck carrying a Maersk container leaves the port and threads through city streets. First on highways, then through dense urban neighborhoods filled with shops and traffic. At night, the same route stays lit with neon signs and heavy commercial vehicles. At another port, a gantry crane lowers a container onto a waiting truck under floodlights, while more trucks queue in line behind. This is the invisible connection between shipbuilding and the global economy. Every container that leaves the port is bound for a warehouse, a store, or a factory somewhere. A container ship's real product is not steel, it is delivery. Every day out of service is money the ship is not making, and every ship eventually goes back to the yard for surgery. When a container ship comes into dry dock, it enters as a working vessel and leaves as a proven one. The entire hull is inspected. High-pressure water blasts the underwater portion clean, revealing anodes eaten by galvanic corrosion, propeller blades pitted by cavitation, and any hull plate thinned by rust below acceptable thickness. Massive components get removed by overhead crane. Workers on scaffolding cut, grind, and weld new plate into damaged sections. Cutting torches throw sparks into the enclosed dry dock all shift. Engine cylinder heads are laid out for overhaul on the shop floor. A crane on a floating platform transfers heavy repair components between vessels and dockside. Every hour a container ship sits in dry dock is money the ship is not earning. That is why yard schedules read like operating room booking lists, pre-planned to the minute and unforgiving of surprises. Not every propeller repair happens in dry dock. For emergency work, a bent blade, a damaged CPP hub, a leaking shaft seal, specialist diver technicians work directly underwater on a vessel afloat at berth. Preparation starts on the dock. Dive helmets, air compressors, cutting torches, welding machines, and heavy lifting straps get staged. Divers suit up in wetsuits, connect surface-supplied air, and descend to the propeller with lift bags, chain hoists, and hydraulic tools ready. Underwater, they loosen bolts on the propeller hub, rig a blade for extraction, and guide it to the surface where a crane lifts it clear. A new blade goes down the same way. Every underwater bolt gets torqued to spec by divers reading gauges through their helmet display, working in near-zero visibility much of the time. Not every repair is out on the hull. Sometimes the surgery happens inside the engine. A ship's engineer uses a lifting bracket bolted to the piston rod, then a crane and remote controller to tilt the piston vertical for removal. The whole assembly comes out of the cylinder liner in one carefully orchestrated lift. Once the piston is out, every ring gets measured and inspected. A caliper measures the free ring gap. A specialized expander tool removes each ring from its groove. The piston crown gets cleaned of carbon deposits with a wire brush. Ring groove depth is checked against the manufacturer's datasheet. Anything worn beyond spec means the piston needs a new part or reprofiling. Skip a ring inspection, and the next voyage starts with a compression problem nobody wants to explain. Reassembly is where craftsmanship meets torque specification. The green hose-like component gets lubricated with red oil before installation. A large piston skirt suspends from chains, and the engineer works around it, applying lubricant to the interior surface with a brush. Screws are lubricated before insertion into the skirt. A shiny piston rod is cleaned and prepared. Guide screws go in first to ensure correct mounting alignment, because getting the rod into the skirt off-center by even a fraction of a degree damages the mating surface. Once the rod is in, every screw gets tightened in a specific star pattern to distribute the load evenly across the joint. Finally, each screw head is locked in place with safety wire, twisted around adjacent screws so that engine vibration cannot back one loose over the years. A skipped safety wire twist can undo weeks of careful work. Engine room repair is measured in details this small, and the industry is now trying to change what fuel goes through all of those pistons in the first place. Every LNG-fueled container ship carries technology first proven on gas carriers. The active vessel, the world's first 22,000 cubic meter liquid CO2 carrier, shows the full construction sequence at a modern shipyard. Steel cutting, keel laying, and launch in April 2025 after months of prep work. Large spherical cryogenic tanks get lifted into the hull. The main engine and superstructure follow. The stern gets its propeller and rudder assembly. The completed vessel goes through sea trials in September and gas trials in November of the same year. On an LNG-fueled container ship, that same cryogenic tank technology sits inside the hull instead of being the cargo, but the engineering is identical. Insulation, double-wall piping, gas detection, emergency shutdown alarms. Every safety system on board exists because a liquid at minus 163 degrees Celsius does not forgive mistakes made even once. Refueling an LNG-powered container ship uses the same procedure shown here. Two vessels moor alongside each other. Flexible LNG hoses connect the manifolds. Ice and fog form on the fittings as cargo flows at minus 163 degrees Celsius. When transfer completes, hoses disconnect, vessels separate, and each returns to service. Fueling a ship should not look this dramatic, and yet. Wind propulsion is coming back, with a twist. A Norse Power rotor sail installed on the Stena Connecta uses the Magnus effect. A spinning vertical cylinder in a crosswind generates thrust perpendicular to the wind direction, adding free propulsion whenever the wind cooperates. Projected savings, up to 9% on fuel and emissions. 2 sails were installed on this vessel. Container ships are getting the same retrofit treatment. Sailing ships were phased out for a reason. Now they might come back for a better one. Not every wind assist looks like a rotor. The Wind Challenger uses a telescoping hard sail made of fiber-reinforced plastic, projected to cut GHG emissions by 8% on Japan to US West Coast voyages, 5% on Japan to Australia routes. Ancient technology, modern materials. The cleanest fuel a container ship can burn in port is none. Shore power lets a docked vessel shut down its auxiliary engines entirely and plug into the terminal's electrical grid instead. Zero emissions in port, zero noise from generators, zero fuel burned while sitting at berth. A mobile shore power outlet unit rolls up to the ship. A worker operates the control unit while the connection arm extends toward the vessel's hull. Thick cables get connected between the mobile unit and the ship's power intake, then between the mobile unit and the dockside power supply. Multiple large connectors lock into place before power flows. Every step requires careful cable management, grounding checks, and load transfer sequencing, because a bad connection on this scale can trip the entire terminal grid. Some ports already require shore power connection for every container ship over a certain size. Global regulations are moving in the same direction, fast. Every container ship is thousands of engineered systems packed into one steel hull. Plates cut and welded, engines assembled and tested, propellers cast and polished, coatings applied, and everything coordinated to keep the vessel at sea and out of dry dock. The industry now faces one major problem: decarbonization. LNG cuts emissions but remains fossil-based. Methanol is expanding, but supply is limited. Ammonia and hydrogen are further away. Wind assist and shore power can reduce emissions today, but the industry still lacks one fuel everyone agrees can scale. Which part of this floating machine should we explore next? Shipyard block assembly, the giant marine engine, the propeller and shaft system, dry dock repair, or future fuels? Drop your pick below. Thanks for watching. If seeing what really moves the world's cargo changed how you see these ships, hit subscribe. The next episode goes inside another industrial world hiding in plain sight. See ya. Take care.